All right, welcome back. Today's topic is differentials, and a differential is just a very small change in x or y. And we're going to refer to them as dx and dy for reasons which will become clear in just a second. We're going to say that dx is an independent variable. We change x by some small amount. And if we think about the idea of a derivative, what we discover is that the very small change in y that goes along with that very small change in x can be calculated by multiplying the rate of change of the function at x with the very small change in x. And that makes dy an independent, or excuse me, a dependent variable. It depends on your small change in x. So this is, again, a linearization. If we think of f of x as some function, and here is my value x, and if I linearize, what I notice is that if this is my change in x and my change in y, that the equation of this line, I can calculate dy by multiplying the growth rate by dx. So let's look at a quick example. This is example 5. And I am given the function y equals x to the fifth plus 37x. And I am told that at x equals 1, I want to make a very small change to x. And therefore, my dx is 0.01. The derivative is equal to 5x to the fourth plus 37. The rate of change at x equals 1, therefore, is 42. And so if I increase x by 0.01, y will increase by 0.42. So the interpretation is that if I am here on this graph, and this is not an accurate graph, it's just a representation, I am at x equals 1, and I want to go to here, which is x equals 1.01, how much will I go up? If we linearize, I will go up by approximately 0.42. Let's look at another quick example. The second one in example 5 is y equals sine of 3x. We're looking at the region around x equals pi, and I want to know what happens if I change x by going down by 0.02. So the derivative of y with respect to x is 3 cosine of 3x. The derivative of y at pi is 3 cosine of 3 pi. And a little quick unit circle calculation tells me that this, therefore, is equal to -3. And therefore, if I go down from x equals pi by 0.02, my y value will increase by 0.06. So down a teeny weeny little change in x, up a little change in y. Again, we're assuming linearization. This is not the actual value on the curve, but it is very close because we are looking at that tangent line. All right, one last example, and this example is going to use implicit differentiation. We are at x equals 2, and we want to change x by a very small amount, 0.05. And notice we don't have to use implicit differentiation, but it's already written as function of x and y, so why not? Our derivative is 1 plus y prime equals y plus xy prime. That's not our derivative. You knew what I meant. The derivative process gives me y prime minus xy prime equals y minus 1. Y prime times 1 minus x equals y minus 1. My derivative is equal to y minus 1 over 1 minus x. And jumping back into here, we notice that 2 plus y equaled 2y, which means that when x equals 2, y must also equal 2, which means that my derivative at x equals 2 is negative 1. Did I get that right? I think so. Yeah. Y minus 2 divided by 1 minus 2. 2 minus, ha! 2 minus 1 divided by 1 minus 2 is negative 1. And therefore, my change in y will equal negative 1 times my change in x, which means that my function, if I increase my x by 0.05 at this point, my function will decrease by 0.05. Okay. Let's see. Do we want to do one more example? I don't think so. I think we are good there. So there's 3 examples of differentials. Last thing perhaps to keep in mind is that you can speed up the process if you think of this as dy dx equals f prime of x, multiply both sides by dx, and therefore dy is equal to f prime of x dx. You can take the derivative, shove the dx at the end of your equation. This is a little suspect mathematically because dy dx is not really a fraction. It's the rate of change of y with respect to x and the limit as change in x goes to 0, but we're going to treat it as a fraction for the purposes of this problem. All right. Thanks for watching and hope you learned something.